Hi everyone, our topic is representation varieties and fixed points. I'm Colin Willette from Carleton College.
I'm Patrick Dendis from University of Florida.
I'm Timothy Charter from James Madison.
And I'm Lior from Georgia Tech.
We're supervised by Dr. David Duncan as a part of the Math and Stats department. Let's get started. So the first thing we want to talk about is what we're trying to do. We're trying to look at spaces called surfaces. What is a surface? A surface is a space that looks locally two-dimensional. What does it mean to be locally two-dimensional? If you look at this torus here in this picture, you can picture an ant crawling on the surface of the torus. And although the torus can be viewed as a subset of 3D space, the ant on its surface only has 2 degrees of freedom for its motion. And you can kind of see this denoted by the lines going around the torus. So even though the torus is curving through 3D space, from the perspective of the ant, it appears to be flat. And we call spaces that exhibit such phenomena surfaces. So other examples include this hollow sphere or that disk, for example. We're interested in results that arise from transformations of these surfaces. And some of the information from these transformations is encoded in an interesting space that we denote with this calligraphic R. We call this the representation variety. This is interesting to us as mathematicians because it gives us information about the surfaces. But it's also interesting to physicists, particularly particle physicists, because we can associate with elements of the representation variety certain types of fields with distinct characteristics. Before we talk about the representation variety in depth, as a little background, we're going to talk about the group S3. The group S3 comes from the quaternions, which are an extension of the complex numbers. So while the complex numbers have one imaginary component, I, the quaternions extend this with 3 imaginary components, which are I, j, and k. And they're denoted by these relations, which you can faintly see, which is I squared equals j squared equals k squared equals ijk equals -1. This was discovered in October 1843 by this guy, Sir William Rowan Hamilton, who famously went slightly crazy and when he discovered this and had to carve it in the side of this bridge rather than waiting until he got home to write in the snowflake. We consider S3 as the set of all quaternions with length 1. So if you think about the circle, this is governed by an equation in 2 variables, which is x squared plus y squared equals 1. Here we have 4 variables, and the equation is a squared plus b squared plus c squared plus d squared equals 1.
Thank you. So as Colin said, we are interested in analyzing surfaces with something called the representation variety. The main idea is that we are going to represent fundamental information about our surface by assigning to each loop on the surface a quaternion from S3. For example, look at this picture of the torus. You can see that there are 2 distinct kinds of loops on the torus. There's the red one that travels all the way around the donut hole, and then there's the blue one, which travels sort of through the donut hole. And we say that they're distinct because if you take one of the blue loops, you can continuously transform it into the other blue loop on that picture, but you cannot continuously transform it into the red loop, and vice versa. Another interesting property is that if you were to take a path that traverses both loops, like say the red loop before the blue loop, you can continuously transform it into a path that traverses the blue loop before the red loop. So in that sense, we say that the loops commute. And so now when we want to talk about the representation variety, we assign quaternions A and B to each of these 2 loops on the surface. And we just established that because these loops commute, we need A and B to commute as well. We need AB equals BA. So in this way, we can characterize the representation variety of the torus. And now that we've done that, we can begin to think about interesting properties of the representation variety. For example, is it connected? If it is not connected, then how many connected components does it have? And by doing this, we can begin to understand pertinent information about our surface or about transformations of the surface that we would wish to understand. And so Lior is going to begin presenting our results.
One transformation of surfaces that we're interested in is the transformation of flipping over a torus around this axis shown in this picture. So this gives us a transformation of the representation variety, and it turns out that the fixed points of this action are the pairs of quaternions in S3, such that each of them are either 1 or -1. more generally, we can think about taking a surface with G holes and taking this transformation where we flip it around this axis, and our result is that the set of fixed points of this action on the representation variety of the surface with G holes is homeomorphic to the set of tuples of 2G elements in S3 such that they're all added plus or minus 1. And we can compute that the number of connected components of this set is 2 to the power of 2G. Another kind of transformation of a surface with G holes that we're interested in is one of order 2G plus 1. Order 2G plus 1 means that if you were to do this transformation 2G plus 1 times, the surface would go back to how it originally started. So on the left here, you can see a depiction of a torus. And to see how this is a torus, picture gluing together the edges labeled A and the edges labeled B. So in this image, we see what this transformation looks like. We rotate each of these triangles counterclockwise by 1/3 of a full rotation. And on the right, we see what this transformation looks like for a surface with 2 holes, where similarly, we would turn this into a surface with 2 holes by gluing together the edges with the same labels. And for this surface, the transformation is given by rotating each pentagon by 1/5 of a full rotation counterclockwise. And this description generalizes to give us this sort of transformation on a surface with any number of holes. And we have 2 results about this family of transformations. So the set of fixed points of this action on the representation variety on this surface with G holes is homeomorphic to the disjoint union of a point and G spheres. And the second result is about this space we denote N sub GK, which is a space constructed from the surface with G holes that we call a circle bundle. And the result is that the set of fixed points of the action on the representation variety of NGK is homeomorphic to the disjoint union of a point with K times G plus the floor of K minus 1 over 2 spheres. And from these characterizations of these fixed point sets, we can compute the number of connected components. So for example, in the case of the set of fixed points of the action on the representation variety of the surface with G holes, we can count that there are G plus 1 connected components.
Okay, so given Lior's presentation of the transformation of order 2G plus 1, we're interested in a particular observation, that if we fold the surface over the symmetries of the transformation, we get this thing on the right called the quotient. So if you look at the top, we've taken the torus and we've quotiented by this transformation of symmetry. Now, this ends up being something that looks kind of like a pillowcase in 3 dimensions. And so we say that this quotients to something that's continuously deformable to a sphere. So we like to say that it quotients to a sphere for short. The idea is that it actually turns out that all of the transformations of Lior's type, 2G plus 1, are part of a larger family which all quotient to the sphere, and we're interested in quotienting to something with more holes. So the idea is that if we take this construction at the top right, and we connect another set of holes, of handles really, onto the surface, then if we pass it back to our original surface, then around the lines of symmetry of the transformation, we've attached that many copies of this transformation, or of this set of handles onto the surface. From this, we can actually build a transformation of the surface that extends the 2G plus 1 action of the surface to a 2G plus 1 action on the handles as well. And we're interested in this fixed point set as well. So the theorem that we have about this on the surface level is that the fixed point set is homeomorphic to the set of 2G plus 1, roots of 1 in the quaternions, and then the 2G plus 1 times the number of holes, power of the elements that commute equal to 1. And then the number of connected components is this complicated formula. Like it says at the bottom, we have a similar result for circle bundles over the surface of the type NGK, like we were talked about previously. We would like to thank Dr. David Duncan for advising us. We'd like to thank the NSF grant that we're on, as well as Joan and Ernest Drum's endowment, and the Elizabeth McConnell Bliss Endowment for funding our research this summer. Thank you.